ठीक से।
ये तो मिला ही था, यही तो था ही।
यहाँ था।
और बताया तो था आपको।
कब बताया, मैं तो पूछ रहा था
तो उस
आपसे।
दिन आप चाय पी रहे थे क्या, मतलब मैंने कहा वहीं था था।
अच्छा, मुझे तो याद नहीं था।
हमारी बात पे ध्यान दो लेकिन।
अरे क्या बात कर रहे हैं। मैं इस चाहते के लिए आज भी बोल रहा था इसको, कहाँ पे मिलेगा करके।
मैंने उनको कहा आप हमारी बातों का ध्यान ही नहीं देते।
अरे ये तो चाय पे आया ही नहीं, आप कब बोल रहे थे मुझे तो समझ में नहीं आ रहा, बट नहीं। अच्छा है, छाता मिल गया, बस वही खुशी है।
So Manjari, we can start now. So
okay, sure.
everyone. So welcome to today's seminar. So as you know, all know that a few days back, the International Pulsar Timing Array has announced the detection of nano-Hz gravitational wave. So this was a huge discovery, and Indian team, Indian Pulsar Timing Array also has contributed significantly. So we'll hear this from Professor Manjari Bagchi. She is from Institute of Mathematical Science, Chennai. So Manjari did her PhD from University of Jadavpur University, and then she did several postdocs, and she spent some time in IUCAD and also TIFR, also in abroad for several postdocs. She joined IMSc in 2014, and currently she is in the position of Professor G. She is interested in mostly pulsars in theoretical and observational perspective. And so we'll talk about more details about the interesting discoveries that was made. So Manjari, the floor is yours. So you could start now, and yeah.
Thanks, Shubhendu, for the introduction and inviting me, giving this opportunity, and thanks everyone. So I think I'm audible well, right?
Yes.
Okay, just give me. I will keep just say. Okay, yeah, I'm in Wi-Fi, so I cannot see the extra ether cord. But anyway, I think Wi-Fi is enough. Usually I connect Ethernet, but that I forgot. But anyway, so let me share my screen first. Can you see my screen now, right?
Yes.
Okay. Okay, so as Shubhendu said, today I will talk about gravitational waves, especially means I will give some introduction because there might be young students who still does not know much about gravitational wave. So after a few introductory slides, I will concentrate on low frequency gravitational wave and one method, particular method of detecting it, which is significantly different than what usually people talk about, like LIGO or LISA, interferometer. And as Shubhendu said, that there is one international effort by international collaboration, International Pulsar Timing Array going on, but I would emphasize the role of Indian consortium. So, elements to understand gravitational wave for the students, I would like to remind you that what is gravitation. So first, in special relativity, we learned that space and time should not be differentiated. Space and time together, four-dimensional entity called space-time. Then we also learned that a mass curves space-time around it, and sometimes people give rubber sheet experiment example and all this visualization effect that if you put a mass on a rubber sheet, it gets curved. Yeah, all is good. We can visualize mass curving space, but mass affecting time is we cannot visualize, but we have to remember that a mass curves the space-time around it, and both massive and massless particle follow the curvature of the space-time. Means the trajectory of a particle, whether the space-time is curved or flat. Flat means vacuum when there is no other mass. So that will just depend, trajectory will just depend the curvature of space-time. It does not matter on the mass of the particles. That is why even light particle follow the curved space-time, and we get exotic phenomena we can observe, like Einstein ring, lensing, and then lensing is the signature of light bending effect. So that is something we need to remember. And also we need to remember that not only means, obviously the first thing is that more massive the object, space-time is curved more. But mass is not the only thing, right? The two objects of the same mass, but which one is denser would curve the space-time more. So if you have same mass white dwarf, say 1.5 solar mass white dwarf and 1.5 solar mass neutron star, so white dwarf would be radius 10 to the power 3 kilometer and neutron star would be only 10 kilometer radius. So neutron star, although that white dwarf and the neutron star would have the same mass, but as neutron stars are is denser, it would curve space-time more. Okay, so that we know. Also, we know that the shape of the object, whether it is properly spherical or oblate, well, in astrophysics, nothing is purely spherical, right? Because everything is spinning, so there is centrifugal force induced oblateness. So that also affects the curvature of space-time. But most of the time, due to calculational ease, we consider the spherically symmetric space-time. But when some object is very rapidly rotating and very dense, like when people talk about rotating black hole, we consider say it is Kermatric. That time, that spherical symmetry is violated. So shape of the object is also very important. And then I already mentioned that motion means I get the meant rotation, but it is not only that the effect of rotation coming from rotation induced shape deformation, but rotation itself can affect the curvature. Means it is almost like some sticky space-time is sticky material around the object. So when the object is rotating, the space-time is also dragging with it. That we call frame dragging effect or lens thinning effect. And then rotational motion is not only motion, there can be vibrational or translation motion. Those also affect the curvature of space-time. And if there is a motion, means something is changing, then say a new star is vibrating. So once it is slightly larger, then slightly smaller, or a star have motion, means presently it is at position X, next it is position X2. So when it was in position X1, space-time was more curved near X1. But when it came to X2, the space-time is more curved in X2 and less curved in X1. And if it is very far, then it is not curved. So, yes, any question? No. Yes?
No question. Somebody.
Okay. Curved, yeah, okay. So, and because of that, we it also induce a wave-like event, right? Which we know as gravitational wave. So we can imagine like when propagating wave-like, so when there is a string of and wave is going. So when it at one point there is a crest, then there is a top. So similarly, we can imagine the gravitational wave means motion of the object generates ripples in space-time, and which you can say squeezing and stretching of space-time, which is known as gravitational wave. And if I think many of you are interested in theoretical aspect, so just in 2 slides, theory of gravitation and gravitational wave. So first comes the famous Einstein equation. So this left-hand side, G mu nu, gives us the information of space-time, structure of space-time, and right-hand side, T mu nu, bears the all information around the mass or matter, pressure, density, etc. And when this effect of curvature means if it is say there was no mass, so right-hand side would be 0. And in the left-hand side, that G mu nu would be replaced by eta mu nu. That we call Minkowski metric for flat space. So when you have a little bit perturbation, a little bit deviation from the flat space, curvature is very small, you can do perturbative calculation. is Z mu nu, you write that metric, you write eta mu nu plus H mu nu. H mu nu is the perturbation of the metric. Then if you do some algebra, and then you can get this equation that far from the source to where the effect of T mu nu is basically 0, which is valid like here on Earth. We say my source of gravitation is of a black hole, which black hole is very, very far. So there the T mu nu of the black hole we can consider 0 on Earth, right? So then you can get this equation, the last equation, that box operator or de-Alembert, and we know this is a wave equation. So that is the mathematics of gravitational wave. And students who are more interested in that Michel Magore's book on gravitational wave is the best book on gravitational wave yet today. And now, after doing some solution of this equation in some special gauge, we call transverse stressless gauge, means assigning some property of the perturbation, we get this like, as we say that it is a solution of a wave equation. And if we assume the wave propagation in z direction, so as we know, we can get a cos omega t minus omega z, this type of function. We could in principle write sine also. And amplitude would be, because it is a tensorial wave equation, we would get this matrix. And you see here where my cursor is 2H plus and 2H cross, those are polarization, which we call plus polarization and cross polarization. We'll come to that later. So this is the basic of gravitational wave. Now, when we get gravitational wave, so say one example, I said that vibration, a star is vibrating. Then the most common source is binary stars. Because when two objects moving around the common center of mass, they are moving and they are emitting gravitational waves. So LIGO detected gravitational waves for some such binary system. And some interesting things happened for this binary system, which emitting significantly strong gravitational waves. Because like electromagnetic waves, gravitational waves also carry energy. And that energy comes at the cost of gravitational binding energy. So there is a binary, it is emitting gravitational waves. So it is losing gravitational binding energy. So the two objects, they would come closer and closer, and eventually they would merge. So this coming closer and closer we call inspiral, and then eventual merger, and after merger there will be a merged object that will be first it's very dynamic, we call that, and then it will be stable slowly, and that coming to stability, that phase we call ring down. Now one interesting thing happened, there are many binary stars, right? Say even in our galaxy, well, we have not detected gravitational waves from our galaxies. Those are we have detected cosmological gravitational wave, but say there are so many binary neutron stars or binary black holes. So they all are emitting gravitational waves, right? So there is a superposition of gravitational waves and some background gravitational waves. So I like to give this example, which you see in this slide in the top two plots. So the left side plot means I throw a stone on a pond. I get a ripple wave starting from the location where the stone went to the pond. Now, when it rains, there are many such ripples. You see the picture on the right side. And those ripples where they meet each other, there is a different pattern, right? That is some, we can call some background wave. The same thing happens for gravitational waves. And so what we recently succeeded to see this type of background gravitational wave in some, as I say, some special frequency range. We have not yet detected gravitation in our frequency range, the single binary event or anything. On the other hand, LIGO in high frequency regime, they detected only many single events. Although they searched for background gravitational wave in their range, their frequency range, they yet have not succeeded to do that. So this is some complementary result. So now my introduction is over. Now I will come more into the real part of the talk. So it is the nature of gravitational waves. So first, this in the middle, you see that the white bar, that is the frequency of gravitational waves, as you know, as we know this day, present day. So you see, gravitational wave can be a low frequency as low as 10 to the power minus 16 Hertz, and then as high as here 10 to the power 4 Hertz. It can be slightly higher also. And there are different sources giving gravitational waves and different range. First, there is early universe and or cosmological origin, which is some just not Big Bang, just after Big Bang. And that gravitational wave can be throughout the frequency range, starting from very low, almost 10 to the power minus 16 Hertz, to be as high as about 10 to the power 2 Hertz. And there are different models. I mean, some people say, okay, maybe different types of inflationary scenario would give different types of this background gravitational wave. Some people say, okay, maybe the phase transition of early universe. Some people say, oh, there are things
Manjari,
like, yeah.
Question.
Yes.
Question. Yeah.
Yeah.
When you are saying that there would be a gravity wave due to the Big Bang, but we do not know whether Big Bang is a spherical symmetric or not. If it is spherically symmetric, how come there is a Big Bang? Means there is a gravity wave.
Gravitational. Yeah. So this what I am saying. Big Bang. It is not exactly Big Bang. Usually, what I was saying, what people say, it is actually from Big Bang model. Following Big Bang model, the other things coming from the evolutionary cosmology, like the inflation potential, how the role of the inflation potential happened. So there are few models in that. Means I was looking at Sriram Kumar's paper, different inflationary potential parameter can give different types of gravitational potential. So yeah, saying Big Bang is oversimplification. So it is the early universe cosmology which is coming out of the Big Bang theory to be consistent with the Big Bang theory, like inflation, early universe phase transition. And then some people think about that cosmic strings, which are the defects in the space-time curvature arised in the early space-time. So those are those are all still hypothetical, and I will show later what our results say about those hypotheses and whether we can improve those hypotheses.
Okay.
So yeah. So because this picture I took, it is from NASA, so it is a little bit oversimplified because in the picture you cannot write so many things, right? Okay. Then there would be inspiral and merger of supermassive black holes. Especially supermassive black holes, we know that there are supermassive black holes at the center of the spiral galaxies, and thanks to all Hubble and James Webb telescope, we have seen inspiraling galaxies, right? So they are also emitting gravitational waves. So, and this supermassive black hole binary merger, you see this where my cursor is moving. So their frequency range lies in the 10 to the power minus 9 Hertz. That is the early inspiral, to around 10 to the power minus 2 or slightly higher. So probably I forgot, means when we think about gravitational wave from a binary source, so the frequency of gravitational wave is twice the orbital frequency. So when the orbital frequency increases, means orbital period is less, means just before the merger orbit is smaller, so orbital frequency is higher, that time frequency increases. So as there is a inspiraling object, it emits gravitational first in lower frequency, then as it comes closer and closer, the frequency of the emitted gravitational wave increases. So see the interesting thing what happens for supermassive black hole binary merger. In the earliest inspiral, the frequency is in the range 10 to the power minus 9 to 10 to the power minus 6, 10 to the power minus 5, which is even lower than LISA range. And you see here in the bottom part, space-based interferometer or LISA, their detecting sensitivity is 1 to 10 to the power minus 5 Hertz. So there, the late part of the supermassive black hole inspiral and merger would fall in LISA band. But the early inspiral of supermassive merger falls in this range. I am interested 10 to the power minus 9 Hertz to 10 to the power minus 6 Hertz. And then we know about the high frequency gravitational waves like vibrating pulsars or supernova explosion or merger of stellar mass black hole binaries, which LIGO have been seen. And interestingly, this cosmological gravitational wave, in principle, each detector should be able to see it. And there is very low frequency gravitational wave, that or a cosmological gravitational wave, which you have to detect through CM. Yeah. Yes, please.
Question related to the supermassive black hole binary merger scenario. So it was basically detected at a very low frequency. So at the earlier phase, but it is also quite lesser than the binary mass black hole of stellar mass black hole binaries. So why is it so? Because the supermassive black hole has comparatively lesser detected in a comparatively lesser frequency than the binary neutron star or stellar mass black hole binaries.
Yeah. So I just said that, see, supermassive black holes, they are of galactic scale, right? So say, like Andromeda and our Milky Way is gravitationally bound. They are inspiraling around each other, right? They are emitting gravitational wave. So their orbital size of the orbit is very large, right? So it takes their frequency is low, and when so as I said, means when they will come closer and closer, the okay, I remember you are saying that, say, when the two supermassive black hole will merge, orbital separation is almost zero. But even then, that will be fall in LISA band, low frequency. But when two stellar mass black hole merge, there also orbital separation is almost zero, but that frequency will be higher, right? Why that difference is there? Is that the question?
No, I think that you answered the question in the first part, that their separation is larger, so that's fine.
Yeah. So that was one part that I think while giving the answer, this also can to that also be confusing, because see, when early part their separation is larger, but when they are merging, two supermassive black hole merging, so that time separation is almost zero. But you see that time the frequency is LISA band. But when two stellar mass black hole merging, their frequency falls in the LIGO band, because there is something called chirp mass, the ratio of mass, that also has some effect to determine the frequency. So that also, but orbital separation is the main thing, but you have to remember the mass also. Okay, any question here?
Yeah,
it's fine. You can
Okay, so as I said that LIGO can detect gravitational wave only in the range of 1 to 10 to the power 3 Hertz. Lisa, 10 to the power minus 5 to 1 Hertz, just lower than LIGO. Then what about the low frequency? You need some different instrument, and we are trying to detect this frequency gravitational wave using pulsars as our instrument. See, pulsars also emit gravitational wave. Actually, when the first binary pulsar was detected, so that it was a double pulsar, double neutron star. One neutron star was pulsar, another neutron star was not pulsar. Maybe its beam was directed in other direction. So they two neutron star orbiting each other, they are emitting gravitational wave. So they are also shrinking. Their orbital period is decreasing. So when this first binary pulsar was detected and observed for some time, and they found that orbital period is decreasing, the only reason for decrease of orbital period, they thought emission of gravitational wave, and they found what if it is really due to the emission of gravitational wave, then what would be the decay rate of orbital period? And that observed decay rate matched exactly with theoretical prediction from general relativity for gravitational wave emission. And that was the first indirect detection of gravitational wave. And that was Hall-Stellar binary. It was done, the work was done in 75 and Nobel Prize was in 94. So it was very fast. But I am not here concerned about the gravitational wave being emitted by pulsars. I am using the electromagnetic waves of the pulsars to detect gravitational waves coming in this nano-Hz frequency range, probably from early inspiral of supermassive black hole, or the superposition of many such supermassive black hole, that background wave, or maybe cosmological background, means whatever is in this range. So that is our intention. And here, as I already mentioned, that about the cosmological origin, mechanism related to inflation, phase transition, cosmic string. Some people are modeling, thinking about dark matter also. So those things means I would mention, would be clear little later, that how we can means detecting signature of background gravitational wave is one thing, and identifying that what type of gravitational wave it is, whether it is a mixture of different origins, so that is another thing. So that also I will come. So I am using pulsar. So just again 2 slides with introduction. What are pulsars? Pulsars are neutron stars, which are end product of stars, which was in the mass range of 10 to 25 solar mass, and as neutron stars are a result of collapse of interior of massive stars supported by only neutron degeneracy pressure, no more atomic structure. They are extremely dense. One solar mass neutron star have radius only in the order of 10 kilometers. So that is why any observable phenomena around neutron star should be explained with the help of general relativity. But there are other 2 unique points, that neutron stars are very strongly magnetized. Their magnetic field in the range of 10 to the power 9 to 15 Gauss, and they are very fast rotator. Spin period in the range of 1 millisecond to 10 to the power 10 seconds. And because of this strong magnetism and very fast spin, they emit electromagnetic beam, like we read in classical electrodynamics in our MSc Jackson, that if there is a, they talk about only electric dipole. So if there is a rotating dipole, it emits electromagnetic beam. This is the same thing. The magnetic axis of the pulsar is misaligned with its spin axis. So when the pulsar is spinning, this dipole magnet is also spinning, and it is emitting electromagnetic beam from its 2 poles along its magnetic axis. And when that beam falls on Earth, we see it. But we have to remember that it is not so easy, because it has been seen that this is a very toy model, because if this was only the case, when you the beam falls, you see the signal, and then you don't see, then you again see, you should see always a delta function like pulse, right? But usually we see lots of feature, and we see on pulsar pulsation in various wavelength, means in optical, gamma ray, X-ray. But remember, all these are clean system. I am not talking about accreting pulsars at all. They are the separate class of beast. So even this simple, say, even if you have two neutron star orbiting around each other, and one neutron star, the beam from one neutron star falls onto Earth, you can see electromagnetic emission in various wavelength, because this toy model is very simplified version. Because outside the neutron star there is the magnetospheric plasma, right, where you have charged particle. So they are accelerated, they travel, then all this what we radiative electrodynamics, we did Bremsstrahlung, synchrotron, all this will happen. So you will see gamma ray, X-ray, they are being generated at different height. Also that electromagnetic beam, we don't know how it looks, because sometimes we here, if you see the bottom left picture, you see some pulse profile can be, sometimes it can be one component with some Gaussian like shape. Sometimes it can be 5 profile, 4 Gaussian. So there are different phenomenological model, but I say those are phenomenological model we still don't understand. But now we don't need to go into the details of pulsar emission mechanism. We only know the pulsars emit electromagnetic beam mostly, and radio wavelength is very clean, and we can we know our atmosphere blocks other wavelengths but does not block radio, so we can detect radio from Earth. So we study pulsars from Earth. So from now on, I will talk only about radio pulsars, which are easier to handle and easier to observe them more accurately. So as I said, that first pulsar was discovered in 1967 by Jocelyn Bell, and today we know 3,300 pulsar. Most are isolated, some are binary. There are few three-body system also. And binaries are very interesting to do other type of gravity study. But in our purpose, means today I am not talking about test of gravity you can do using binary pulsar. Today I am only using pulsars as stable clock, means they just emit electromagnetic beam, and we are supposed to see the beam once in every spin period. Other than that, we don't need to bother about any other physics related to pulsar. Now, as I say that we should see the pulse once in every spin period. But say the rotational period of a pulsar is 1 second. So the pulsar is emitting the beam in 1 second interval. But each of the beam reaching the Earth after some light travel time, right? And if that light travel time is same always, say if the distance between pulsar and the Earth is a constant d, and speed of light is c, then d by c. If that light travel time is constant, so I mean the pulsar which is starting at the x second, it will reach at x plus light travel time. Next one is again another light travel time. So on Earth, if you subtract the consecutive time arrival time, that amount it took light travel time, so it will get cancelled. You will get the real spin frequency, right? But that is not so easy, because this is very simplified. The distance between pulsar and the Earth are not the same. Pulsars are moving because they got some kick during their birth due to supernova explosion. Then if it is a binary pulsar, there is orbital motion. Then the Earth's motion around the sun, sun's motion around the center of the around the Milky Way center. So everything we have to take care. And we know very good planetary ephemeris, which includes the motion of the Earth. So we can take care of all this. And another thing we have to consider, not only this classical concept, but we have to deal with the gravitation, means general relativistic effect. So when you have a binary pulsar, there is a companion. The signal from the pulsar is coming very close to the companion. Then the extra curvature of the space-time near the companion, that also you have to take care in this modeling when the signal should arrive on Earth. Then what happened when, if you think about galactic scale, our solar system is very compact. When the signal from a pulsar coming to Earth, many times it comes very close to other planets, especially, and then even if those are planets, but space-time curvature around those planets also affect. Means those effect is very tiny, but we are doing very precise experiment measurement, so that we have to take care of. So all this means mass of the planets, all this we use the planetary ephemeris obtained from JPL, Jet Propulsion Library, and we model all this. Also, we need to model the effect of interstellar medium, right? Because it is not vacuum between the pulsar and the Earth. Through ISM, light is not traveling with the speed c, it is traveling with the group velocity. So that we take care of, and we get something called dispersion measure that I'm sure all of you know. So all this we include our model. What do we do? See, if the pulsar is basically, in principle, you should see, say, a pulsar is spinning in spin period is 1 second. So you should see consecutive pulses in 1 second interval. But you will see it is randomly, means it is not in 1 second interval, sometimes arriving earlier, sometimes later. So we model, say, I have 10 observed time of arrival when the pulse arrived, and we fit all this model parameter to see to predict why this discrepancy is coming. Now, say I have a model from my 10 arrival times. So then I can predict when the next 10 pulses should arrive. Then I keep on observing. So I have some predicted time, I have some observed time, and we compare them. If there is discrepancy, we fine tune our model. And then after all fine tuning, there still will be a discrepancy. Means a difference between the model arrival time and the real observed arrival time. And that difference is known as residual. And as pulsar timers, our main motto is to get residuals as good as we can. So this plot here, x-axis is just the number of data points, and y-axis is the residuals you see in millisecond order. And this is taken from a textbook. It was published in 2002 or something. That time, having residual in the order of millisecond used to be considered very good. But today we are getting microsecond or even sub-microsecond order residual, because our models are very good and our telescopes are more sensitive. But one thing I would like to point means the same technique is timing analysis technique is used by X-ray pulsar people also. But X-ray pulsar means the accretion mechanism is so unpredicted, means there you never can get residual better than millisecond order. So in that way, our radio pulsar are better timer. You can get very small residual, and that why I am emphasizing on getting very good residual, because these residuals are the things which carry the imprint of gravitational wave if it is there. Why? Because every other thing which is affecting space-time between when the signal is coming from the pulsar to Earth, I have taken care. But if there is gravitational wave, means squeezing of space-time between the pulsar and the Earth, that will also be affecting when the signal arrives in the Earth. So that is what we are trying to do. Now we'll say, okay, I am observing one pulsar, and I expect that if I observe for a long time and this iterative way I am improving my timing model, the residual should be very good. But no, as we all astronomers, we know there are so many uncertainty, instrumental noise, and intrinsic noise to the source. Then there can be glitch, starquake-like event. But there is one thing. If I observe 60 pulsar, and if I see something, some correlated effect in the residual of all 60 pulsar observed by various telescope, then we cannot blame on a noise of the telescope or noise of some pulsar. So then it would be due to gravitational wave, because these gravitational waves are coming from very far, right, from other galaxies. Or even just cosmological origin, even very, very far. So all the pulsars that are in our galaxy, all of them would be affected by the same gravitational wave. So that is why we do not observe only one pulsar, we observe a number of pulsar. And we correlate their the residuals to see if there is a signature of gravitational wave. So this is again just some pictorial depiction. Means here is the Earth, signal from various pulsar is coming, and there is background gravitational wave. Now little bit at equation, means how this, the mathematical relation, how this residual depends on this gravitation. So just let me go in this slide. You remember the gravitational solution of the wave equation? It was like this. So there was that polarization, means amplitude of the wave, H plus or H cross. And using that, means if you do the derivation, this perturbation, that polarization amplitude, H plus and H minus, that would be different on pulsar and on Earth. That difference, say it is delta H. And it will be delta H for plus polarization and delta H for cross polarization. And say there is one, first let us forget the background, stochastic background. Say one gravitational wave is coming. So the initial frequency of the pulsar is, say, nu-0, means spin frequency. Because when we do timing analysis, we try to get good residual, we are mostly considering the spin frequency of pulsar, right? We see the pulse once in every rotation. So you say one pulsar, you have spin frequency nu-0, but because of this space-time squeezing and stretching, it would appear to us the spin frequency of the pulsar would appear as nu as a function of t much time, because this gravitational wave is a time-dependent thing. And this is the relation. You will ask what are alpha, beta, gamma. Those are the direction cosine of the vector from the pulsar to solar system barycenter or observer. You know that as the Earth is moving around the sun, we try to correct for it by converting, translating our all time measurements to solar system barycenter, which is a local inertial frame. So that is why this vector from pulsar to solar system barycenter and direction cosine of that vector. And so that equation, then you can define as our convention a redshift parameter, right? Nu t fractional difference, nu t minus nu-0 by nu-0. So nu-0 is the original frequency and nu t is the changed frequency due to gravitational wave. And that you see difference on, obviously on t, and there is another omega. So omega is the direction of gravitational wave, because I said that I am now considering only one gravitational wave. Now, if you have a stochastic gravitational wave, that means there is a uniform background throughout the sky. You have to do this integration over omega, all the direction. This is actually a 4 pi integration. So then you get the total redshift of the spin frequency of the gravitational wave. And then depending upon how long you are observing, you get the residual by integrating the time. This is that equation 1.55. So if you are very interested to understand all step-by-step derivation, you can see either that first paper, De Twiller in 79, but even better, this Chiara Manjari's PhD thesis, which is available in Springer PhD thesis. So that is very detailed. So because it is not possible for me to go into detail. So I would like to summarize that yes, I think I could convince that if there is a gravitational wave, that would affect our residual. And as I said, if I have only one pulsar, I cannot say that the residual is, how much the residual is due to intrinsic noise of the pulsar and how much is due to gravitational. We observe a number of pulsars. That is why we call pulsar timing array. We are doing timing analysis of pulsars, but not a single pulsar, and an ensemble or array of pulsars. And now, again, there is some theory which I cannot derive now, but you can see the original Hellings and Downs paper. It was 1983. So say if you have pulsar A, you are observing 100 pulsar. So you have, for each pulsar, say you have 10 residual. For pulsar A, you take first residual. For pulsar B, you take the first residual. You multiply the value of the residual. Then again, you take the second residual of pulsar A, second residual of pulsar B, you multiply them. So you keep on doing this. So you then you sum all this. So you get the one number, and that number should theoretically depend only on the angular separation between the two pulsars. So this angular separation is given by this relation, that zeta theta, which depends, you can see this expression. I'm sorry, this is not very clean slide. You see x log x, this relation where x is this function which depends on cos theta. And this zeta theta function, it will actually look like this. Here, this red curve. So x-axis is the angular separation between pulsar and y-axis is zeta theta. And that would be the same whenever there is a gravitational, background gravitational wave. It does not depend upon the nature of the gravitational wave, or the nature of the background gravitational wave. Remember, we have already integrated over the whole sky. But there are different types of background, right? I said it can be cosmological origin or from astrophysical origin, superposition of many supermassive black hole merger. And even there are many cosmological models. So that will actually come as an amplitude. You see this, there is another function, sigma square, and where sigma g for gravitational wave, sigma z, it gives, this is a square root of this integration. F is the frequency of the gravitational wave. So this function phi, that bears the signature of the property of the background gravitational wave, as well as the intrinsic noise of the pulsar also. If it is due to intrinsic noise of the pulsar, the phi function would be like this, which I say phi CURN. CURN stands for common uncorrelated red noise, because I am saying it is pulsar to pulsar property. So this will be uncorrelated. This A is some amplitude, F again frequency, and it is some kind of gamma log minus gamma. And then there is, if it is due to gravitational wave, and it can be both, then there would be a summation of both phi function. And the form of phi function, if it is due to gravitational wave, which I say phi HD, the same form, but the amplitude and that power law coefficient would be different. And this what will be this gamma HD, means gamma gravitational wave coefficient. Again, if this gravitational wave is for cosmological origin, it will depend on particular model. Actually, a few days ago, I was talking with Sriram Kumar. He is actually working on one aspect of cosmological gravitational inflationary scenario. Even then, he can get a number of various values of gamma by changing some parameters of inflation. And now, if you invoke other scenarios like cosmic string or phase transition, which I don't know very well, so you can get various values of gamma. But in astrophysical origin, the calculation is much simpler, and I can show you some reference where people know that if it is you get a background gravitational wave due to mergers of many supermassive black holes, this value of gamma would be 4.33. So I will tell you what we have seen and whether we can say something about the origin. Now say I am observing it's 60 pulsar. Actually, presently international collaboration is observing total 80 pulsar. And see, this function depends on theta, right? So there can be, say, when the value of theta, say I choose the value of theta 20 degree. So there can be many pairs, right? Pulsar A and B, pulsar W and V, whose angular separation is 20 degree. So if this sigma G was constant, all pairs which has the same angular separation would give the same this correlation function, right? They would probably fall either they would, depending upon the value of sigma G, they would either be top of this red curve or bottom of this red curve, right? But this sigma Z has that phi common uncorrelated red noise contribution, which varies from pulsar to pulsar, right? So all these pairs, although value of theta is same, they will give different values of this correlation coefficient. So you will see various points, but as that sigma theta function dominates, those points will be clustered around this red line. The red line, as I say, it is just this sigma theta function. And we are trying to see whether we see this signature of this red curve, which we call Hellings and Downs curve, and this relation, Hellings and Downs correlation, based on the people who first proposed. And well, this slide is little old, 2 years old. Now we have more pulsars. In the right-hand side, you see sky map of pulsars. The gray ones are the total pulsars being observed by various groups, and the red ones are our Indian collaboration observing. So now you would say, what have we seen? Means we did some announcement like last month. Have we really seen this Hellings and Downs curve? Let me show you our result. But before that, I would say, okay, here I have scattered plot, right? You can easily convert it to a histogram. You have number of pairs, and depending upon number of pair, what is the various values are giving. And you can do box plot, right? For say when angular separation is 20 degree, various pairs are giving various values of correlation function. What is the median value? So that combination is we draw violin plot. I know you know it is a combination of box plot and kernel density plot, where in bars of in histograms you replace by Gaussian kernels. So this is the three group results from three groups. I will tell you what these groups are, but first let me tell you the results of three groups. So for the time being sake, first one is blue group, then orange, and then green. Actually, this is American, then it is European and Indian, then Australian. And each case you see in the black, that is the theoretical zeta theta line, helix and downs curve, and then you see this violin plots. If it was a very good detection, we'd say the middle of the violin, where it is the thickest, which has the median value, it should fall on the theoretical curve, on the black curve. But we don't see that. Not the American result, not European Indian result, not the Australian result.
Australian
But,
result is better, no? It's more,
huh?
the Australian result is better. More.
Yeah, it is slightly better here, but it is off at the end. So actually, if you read the paper, means everyone is actually around 3.5 sigma. It is none of us have reached yet 5 sigma. So, but it's probably will reach soon. And another thing I would like to show you, means in the middle plot, in the European and Indian result jointly, means this is a helix and downs curve, but here you see there is another plot where the x-axis has the gamma, and this dashed line, that is for gamma 4.33. And you see here also you have two colors, means in the violins also you see two colors, but they are mostly overlapping. Because there are two things. Means Europeans are doing this experiment for a long time. They started from 2008. So we did one, means we kept full European data and added Indian data. Then we deleted some of the Europeans themselves were skeptic about their old data. So we omitted some of the old data. Then we realized, means if we keep the full data, then our result hints that gamma was close to 4.33. And if we keep only the new result, then gamma is much smaller, around 2 here, around 2.5. So if it is closer to 4.3, means it is supermassive black hole origin. If it is lower, then cosmological origin. So this is still we cannot confirm what is the origin, and if there is mixture, how much is the mixture. So that is why if you carefully read the papers, we never claimed that we have detected gravitational wave. We see that we see hint of gravitational wave, or we see early signature of the gravitational wave. And few months ago, actually it happened for last 2 years. There was a detection committee, means detection committee of Pulsar people that consisted of 2 people from Pulsar background, few people from LIGO background, and some people from Planck, means cosmological background. They have actually set some checklist that when we should say that we have detected gravitational wave, because none of us want to be the bicep. So that is why. But we also wanted to publish this result because we see the similar thing in 3 different data sets. You would say why it is an international consortium, why we don't combine and do the analysis on the combined data. This is ongoing, but see, if the data is combined and then you do the analysis, if there is something wrong in the analysis, it would be difficult to detect. But first, independently, we saw, yes, there is a signature of gravitational wave in the independent data set. Now, when we combine, we are more confident that we will see better detection. And again, this was actually, I was checking 2 weeks ago, that even in less than a month, there are many models about what are the origin of gravitational waves. Means I think cosmologists are in a spree to explain all their various favorite models. So that as I said, that even the detection is not in 5 sigma, so I don't want to go to that implication, but I will come to some to what we can do in the future. Now let me tell you some details about this international collaboration. As I said that it is on international collaboration. Okay, no question. We signed the treaty. So this is called International Pulsar Timing Array. So the first experiment started in Australia in 2004. And that is the main reason their result is good, because as I was saying, this analysis is from residuals, and residuals come from iteratively modeling your all timing parameters, right? The longer you observe your pulsar, the better would be your data. So Australians started in 2004. They are known as Parkes Pulsar Timing Array, as their main telescope is Parkes telescope. Then in 2008, North American Gravitational Wave Observatory started. Their main telescopes were Arecibo, Green Mac, Very Large Array, and Chime. Well, Arecibo collapsed few years ago. Then next year, in 2009, came European Pulsar Timing Array, which had a few telescopes in few countries like Effelsberg in Germany, Lovell in UK, Sardinia in Italy, Nanke in France, and Westerbork in Netherlands. Westerbork also is not operating for last few years. Then we started very late in 2015. Then you will say, okay, as I just said, that data quality is better if you do the longer observation. Then you should expect our Indian data to be much worse than Australian or American or European data. Yes, we were, means up to last year, we were not as good as them. And that is why when we started, we could not join immediately the international consortium. For first 3 years, we were associate member. And when we showed them our result and we applied, we become full member in 2021. But there is one advantage, because of some special feature of GMRT, it is so sensitive that although we are a baby collaboration with respect to other international collaboration, our data quality is today as good as them. So because we know that a few features of GMRT, GMRT is not a single dish. It is an array of antenna. There are 30 antenna, each 45-meter diameter, and we know it is a Y-shaped array located near Pune. And there is another advantage, that GMRT can observe very broadband. There are actually 5 frequency band. One is very low frequency, 100 to 250 megahertz band. Then there is 250 to 300 megahertz. Then around 500 megahertz. Then about 100 to 1.4 gigahertz band. And as it is an array, you can do something very interesting. Means, you can divide it into 2 sub-array. Means you can use 15 antenna in one band and another 15 antenna in other band. So we are observing 22 pulsars in band 3 and band 5 simultaneously. And because this ISM effect, which is the propagation of electromagnetic wave with group velocity, that depends on the observing frequency. And as we are observing, doing simultaneous multi-frequency observation, we can model out the effect of interstellar medium very well. So that actually helps us to lower our residual in a shorter timeline. So that was advantage, and thanks to the vision of Govind Soru, we have GMRT. So I would say something more, and our data is now almost as good. Means our in-PTA data alone is almost as good as the joint data of Australia, Europe, and North America, that I will show you some plot, is almost, not exactly good, but our in-PTA data is as good as any individual PTA. And recently we added, combined our in-PTA data with European data and did the search of gravitational wave. And before that, there are a few other things. Means one thing is that our NPTA data itself is public. So if you want to do some other science, our residuals are and parameter files are public. So if you want, you have a new model for gravitational wave or new technique of searching gravitational wave, you can freely download the data and do your own search. And our residual may not be the best, means it is in the same order of other PTAs, but we can do the best DM measurement ever, because what I just said, that simultaneous multi-frequency observation. And something else also happened very interestingly. It means one of our pulsar was once in such a way that sun fell onto the line of sight of our pulsar. And that is why through in the pulsar signal, we could detect the signature of coronal mass ejection in 2021. That I'm just telling you to say that when we try to do pulsar observation, we can sometimes get very exotic, means auxiliary science also. That has nothing to do with gravitational wave, but we can do something good.
Manjari,
now what? Yes.
2 minutes.
Yeah, sure. I'm almost done. Next few slides are very small. So here in this slide, I will just substantiate what I see. This is our NPTA result in 2020. So you see our residuals in microsecond order. So you see the first pulsar in the top left corner, the residual was in the order of -50 to +50 microsecond. And it was IPTA data in 2019, means joint data of North America, Europe, Australia. The same pulsar is here, the second column, second row. You see the residual in the order of +5, -5 microsecond. So only one order of magnitude, and now we are the same. And this is some coronal mass ejection plot. So what we saw, sudden increase of DM due to coronal mass ejection. And this is our DM measurement. It was very good. And just a little bit technical detail. So it's boring information that what are the institutes involved in Indian collaboration. We are using GMRT, which is done by NCRA, but people are everywhere. IMSc, TIFR Mumbai, NCRA, RRI, IIT Hyderabad, Roorkee, BITS, Pilani, ISAT Bhopal. Also, we call it in PTA, Indian PTA, because the GMRT is Indian, but we have colleagues in Japan, Kumamoto University, and there are members in every stage of career. And we are very social. You can see our website, follow us in Twitter or Facebook. And I would also like we like Americans or Europeans and $1 billion funding. We are running this experiment for almost last 9 years without a single separate funding, just because all our institutes are providing support and we are using each other's cluster, like all 40 members has access to NCRA cluster. So thanks to all this institute, it is a truly joint collaboration. And this is the picture of our members, and you know everyone. You can see, and he is the soul of this experiment. Bhalchandra Joshi, we call him the youngest member also. Without him, we could not come here. So he is so energetic and so enthusiastic, and you see some postdocs, some PhD students, some undergrad. So what is the future? As I said, now data combination is happening. North American, European, Indian, and Australian data is being combined. And the plan is to do gravitational wave search in the combined data. And it is not that we are only working on the data we have. We are continuing observing pulsars and doing data analysis. We are in every GMRT cycle, we are writing proposal for observation in the next cycle. Our hope is that we will see better HD curve, means 5 sigma detection probably within next 2 years. And remember, we have seen only HD curve, which is background gravitational wave. we have searched for other types of low frequency gravitational, single, individual inspiral or bursting source that we did not see anything, but hopefully when this combination is done, we will see other types. And there can be more astrophysics. If it is in supermassive black hole origin, it will help us to understand the evolution of supermassive black holes, that in spiral phase, how they evolved. And if it is cosmological origin, people can tweak their cosmological model and understand that early universe better. And there are 3 associate members in Pulsar Timing Array. One is South African, we call them MeerTime. They use MeerKAT. There is Chinese group. They are using their first telescope. Actually, they also have seen the hint of helix and downscarp. Then there is a very small group in Argentina. We are hoping they will also join collaboration soon. And there will be some auxiliary science, maybe better model for interstellar medium, better model for planetary ephemeris. That actually very important, because we, as I said, that our timing residuals, you need to model them using the ephemeris of different planets, right? Because their mass and position also affects extra curvature of space-time. In 2012 or 13, actually North Americans thought they have detected a burst of gravitational wave, but then they actually realized if they change in the planetary ephemeris file, the Jupiter mass little bit, that signal was going on. Then they talked to the Jet Propulsion Laboratory people, they checked their data and they realized, yes, the mass of Jupiter was slightly incorrect. Then they corrected it from the feedback of North American Gravitational Laboratory. And you know, those planetary ephemeris will be very important in the future, when probably we'll have interplanetary travel and all these things. So there are lots of auxiliary science will come. So and this is something about the evolution of supermassive black hole. There are different astrophysics input which we can pinpoint in the future. So today we cannot do anything. So here I would stop by showing you this picture. It was in this February, when we are organizing a busy week, means when all in PTA members from various institutes, we were all gathered in IMSc and worked very hard only on in PTA work for 1 week. And that time we realized that our data could be combined with European data and we could see the signature of Helix downscarp. So you see all smiling face even after days and nights of work for 1 week. So we are all very happy and we can promise there will be better result very soon. Okay, thank you for your attention.
So let's thank Manjari for this talk. And now some more questions. Yes, sir, go ahead.
Yeah. So, ma'am, as you mentioned, LIGO can detect gravitational waves in the frequency range of 1 to say some 10 to the power 3 hertz. Okay. So this is the frequency range of gravitational waves that are generated through pulsars and supernova explosions also. So is there any specific reason you haven't detected any gravitational waves from supernovae?
Yeah, I think it is a single source. So means, see, not only the frequency, you have to consider the magnitude or characteristic strength. So what is the strength of those gravitational, or they have searched. Also, they have searched continuous gravitational wave due to the spin of pulses, because when the pulses spin, they become oblate, right? They have quadrupole moment. They are also emitting continuous gravitational wave. So yes, LIGO has not succeeded to see a gravitational wave from supernova or from pulsars. So one thing is that they are it is a bit noisy, means detection sensitivity of the instrument is different in different types of gravitational wave. So they are probably when the Indian LIGO will join, and there will be, I think they call LIGO 3 generation 3 LIGO or Einstein telescope, which is a super LIGO. So hopefully they will detect that time.
So, Manjari, it's a nice talk. So, thank you for.
Thank you.
Yeah, sorry.
Thank you. Yeah.
Yeah.
Okay. Say.
You should come here. You already sat in one or two interview boards. But
I'll try to visit. Actually, here means too much teaching and then all this in PTA work. So, but I have never been there, so I really want to be there.
Okay, now a science question. So, nano-Hz gravitational wave is essentially a background gravitational wave, right?
No, there would be a single gravitational wave, but that we have searched for it, but data is not yet sensitive to detect the single like one supermassive black hole inspiral. That wave is also there. But that we have not detected yet. We only detected the superposition of the background wave. Means if it is
Now I understand that if there is a single gravity wave passing, then what it will do, it will at one round it will stretch in certain direction and squeeze in another direction, and in the next cycle it will just do the opposite, and therefore the time that it takes from a light from pulsar to reach us, that will be varied, and from there we can detect a gravity wave. Okay, I'm talking in principle. Okay, forget about the technical details.
Yeah.
Now, if you have a background gravity waves, which is superposition of all kinds of gravity waves, then it is essentially a stationary wave solution, right? So, in the stationary wave solution, will it actually stretch in one direction at certain time, and it will stretch in another direction in another time? Will that? You understand?
Yes. Yes, we are. What I say, stretching and squeezing, that was a very toy expression. But here, actually, we are just that is why I showed that expression. Means it is coming basically that metric perturbation h mu nu because of gravitational wave will be different and at different place of on our galaxy. It's at different location. The value of h mu nu would be different.
No, that is fine. That is okay. Yeah. So that's what we know, that in gravity waves it is quadrupolar and then it stretches in one. Therefore, LIGO has this L arm. Okay, but
no.
I'm trying to figure out if the gravity waves now superpose. One wave coming, one wavefront coming, I understand. But if it superposes, it will be a kind of a stationary wave solution, of course, complicated by the two polarizations of H cross and H plus. So will the expectation what we have about gravity waves hold? Because in different directions, will it actually do that, stretching and squeezing, alternate stretching and squeezing, that creates that gravity wave signal?
I understand. Yes, you are right. That is why it is actually not see what you are saying. We are the calculation you remember how LIGO people calculate the strain, that delta L by L means change in length. Our calculation is not in that way. Means that is why we need to consider how the frequency is changing. It is difficult to explain without blackboard. So what you are saying, it is basically, I stopped sharing. Just let me start the sharing once more. Yeah. So okay, you can see this slide, right?
Right.
Yeah. So here this is that metric perturbation is means see here, first we means the way the calculation comes. First, it is we consider one gravitational wave coming, and it is not that they are being superposed and then the stationary wave coming. Means there are gravitational wave coming from each direction. They are each affecting the pulsar. So see, for one gravitational wave, the effect is like this. You can get that redshift function that depends on the direction of that individual gravitational wave, right? Then there is gravitational wave from each direction. So we do the integration over the direction. So it is not that first you superpose the waves and then you see their effect. Means the gravitational waves are coming individually and then they are giving the effect. So as if it is isotropic and other properties of the gravitational wave is same. So that is why the integration is just over the direction here.
Okay. Understood.
Mm-hmm.
Hello, ma'am. I have one question.
Yeah, sure.
You have chosen pulsar as your object to detect the gravitational wave. So
Yes.
can we use other time critical objects like FRBs to detect the gravitational waves?
FRBs are transient, right? One burst, then it is gone. How can you do timing them for 10 years or so? You cannot model them, right? You need something. Yes.
Okay.
It's a cosmic clock, right?
60 minutes में
Yes.
Okay.
So are you guys monitoring the same objects again continuously, or including more number of objects?
Yeah, so GMRT is very competitive. So actually for last 2 years, we were trying to increase our number. Actually means because we ask for each cycle 200 hours, our proposal goes to 5 referees. And a few times referees asked why you are not increasing, you are getting better and better result, you should increase number of pulsars, but GTAC is not giving us more time. So this year also, we just submitted proposal on 15 June. So 15 July. So we have asked for more time. If we get more time, we will increase the number of pulsars.
Even BC cannot do that. BC Joshi.
Even Joshwant Gupta is there, and once actually means how GMRT works, it is too strict and too competitive. So once means not this proposal, I was involved with another small proposal with Joshwant Gupta, and he was center director, and his proposal was rejected, and that mail ended with. Dear Joshwant Gupta, your proposal is not competitive enough, so we are rejecting your proposal. We hope you will remain interested to GMRT. So the GMRT is oversubscribed and it is very good.
Okay.
I have.
Okay, go ahead.
Yeah.
Ma'am, can you please comment on the factors that determine the amplitude of the gravitational wave? Is it only the mass and radius of the object or something else?
No, it's not.
Yeah, it is actually a bit complicated. It is not the mass. So if it is a gravitational wave due to a binary object, then orbital separation sometimes and eccentricity also should come in principle, but usually we think when the gravitational waves come very close to our close to merger, they become circular orbit. So Gopakumar in TIFR, he is trying to incorporate the effect of eccentricity. So even if you that should in principle determine, and then masses.
Okay, so let's thank Manjari for the wonderful talk, and we hope you could visit us here sometime later once you have.
Yeah, yes, thank you.
Okay, so.
Okay, thank you.
For today.
Okay.
Okay, bye.
Yeah, bye.
Bye.
See you.
Basically, for a neutral